Let E be an equivalence relation on a set X. So E is a subset of X cross X that has the properties of reflexivity, symmetry, and transitivity. We create a partition out of it by considering the set of all equivalence classes of elements X of big X, where the small x ranges over the entire set, big X. So for every small x in big X, there is one equivalence class, but it could be so, of course, that different small x's create the same equivalence class. The set X over E is called the quotient set of X by the equivalence relation E. In this video, we're going to give a formal proof of the fact that X over E is always a partition of X. There are three conditions that define a partition. For P to be a partition on X, recall that the following properties need to hold. I'm going to put the two conditions into one condition here. For every element A of P, we must have that that element is, first of all, not the empty set, and secondly, it must be a subset of X. This condition is clearly met in the case when P is the partition, or to be checked partition, created from the equivalence relation. Why? Because there, A would be one of the equivalence classes. But how is an equivalence relation generating an equivalence class? How is that concept defined? When equivalence class of an element X is the set of all possible elements in X such that the pair xy is in the E relation. So for this A, we need to check two things. One, that is not empty. How do we know A is not empty? Well, for it not to be empty, it needs to have an element. X itself is an element of A because by reflexivity of E, the pair XX belongs to E. And therefore, since X is also an element of capital X, of course, reflexivity only holds for the elements of capital X. Both conditions here of Y being in capital X and the pair XY being in E are fulfilled. Therefore, X is indeed an element of its own equivalence class. This equivalence class being A and X being an element in there confirms that A cannot be empty. It must have small x in it. Great. Now, how do we know that A is a subset of X, which is the second thing we want to check? For the A can't be empty and it has to be a subset of X. Why is A subset of X? What is our A? Our A is equivalence class of X. And if you look at the definition, this set consists of all those y's from X such that some property holds. So the only elements of this can be those that are elements of X with an additional property, but what counts here is that everything in here must be an element of X just by the way the set is defined. So if I pick any element Y in A, then such an element will indeed be an element of X just by the definition of A as the equivalence class of X from this part of the definition, to be specific. So we've now confirmed that the first property that describes a partition does hold in this case. The second property is that for every X in capital X, there needs to be exactly one element in P such that X is an element of it. Let's see if this is true. If I pick a small x in capital X, well, firstly, to show that there is exactly one A, I need to find one. First, I need to show that it exists. We could maybe pick the equivalence class of X as our A. Will it work? Well, we already saw earlier when we were checking the first property that small x is indeed an element of its own equivalence class, and hence of A. That is exactly what A was required to do. It was supposed to contain the small x, and it does. So we found that for arbitrary x, we can indeed find an A having this property that x is in A. But that's not enough. The exclamation mark here indicates that such A must be exactly 1. In other words, there can't be two of them. So let's suppose we have potentially two such A's, call them A and A prime. Well, the first A we already have, it is the equivalence class of X. So then we can consider a possibility of a second A and call it A prime. What we know about that A is that X is an element of A prime. What else do we know about A prime? Well, we know that A prime comes from P. What is P? Here we propose the partition P to be X over E. Of course, we're still checking that it's a partition. But the point is that the elements of the P we're working with are equivalence classes of elements of X. So this A prime needs to be one of those equivalence classes as well. Let's say it's an equivalence class of some element X prime, where X prime will be from capital X as well. So now we have that the element X being in A prime is also in the equivalence class of X prime. But what does that imply? Recall that the equivalence class of an element is defined as the set of all those y's that are related to that element. It's the set of y's in X such that the pair X prime Y is in E. Small x being one of those y's implies that X prime X is in E. Somehow this should imply that A prime equals A. Let's see how this is possible. To show that A prime and A are equal, we have to show that they have the same elements. Two sets will be equal exactly when they share exactly the same elements. So let's investigate what are the elements of one and see if we can conclude that all of them will also be the elements of the other one. Let's pick a random element y in A prime. What do we know about y? Well, if it's in A prime, which is the equivalence class of X prime, by the definition of the equivalence class, such y will be related to X prime by the equivalence relation. So we can conclude that X prime y is in E. What we also know, as we've already shown, is that X prime X is in E as well. We know that X prime X is in E as well. Now we can use the property of symmetry of equivalence relations to conclude from here that X prime is in E. Now observe, X prime being in E and X prime Y being in E gets us that by transitivity, XY is also in E. But if XY is in E, that would mean that Y is an element of the equivalence class of X, which is exactly our A. So we obtain Y is in A. That's exactly what we wanted to show, that every element of A prime is also an element of A, except that not quite. We also want to show the other way around, that if I pick an element of A, it will be an element of A prime as well. So far what we've shown only confirms that A prime is a subset of A. In order for them to be equal sets, we want A to be a subset of A prime as well. To show that A is a subset of A prime, we follow a similar strategy. We pick a random element Y in A. Because A is the equivalence class of X, Y being in A implies that the pair xy is in E. At the same time, we also have that x prime x is in E. Let's write that down. X prime x is in E as well. By transitivity, x prime being related to x and then x being related to y, we can conclude that x prime y is in E. That is exactly the condition according to which the equivalence class of x prime is formed. So then y must be an element of the equivalence class of x prime, which is exactly our A prime. Now, assuming that y was in A, we were able to conclude that that same y is in A prime. That shows that every element of A is also an element of A prime. In other words, that A is a subset of A prime. These two properties together, that the A and the A prime are subsets of each other, they allow us to conclude that A prime and A are equal, just as we wanted. So by considering an arbitrary A prime that also has x in it, we were able to show that that A prime must be equal to the A we initially proposed to have x in it, which was the equivalence class of x. This shows the uniqueness part as well. Initially, we showed that the A exists by building it as the equivalence class of x, and afterwards we showed that such A is indeed unique by confirming that every other A prime having the same property of containing x must be equal to it. So we have proved the second property of being a partition, and now that we have both of these properties, we can see that indeed, from an equivalence relation, we get a partition. This partition has its blocks, the equivalence classes of elements of x. If you'd like to understand the intuition behind equivalence relations and partitions, watch the other videos which answer the question, what is an equivalence relation and what is a partition?